Hey guys, so we can definitely say that binomial expansions is not the hardest topic that shows up in IB Math. And by the way, this is a common topic for both the SL and the HL courses. However, there are a few types of binomial expansions problems or exercises that you need to know how to go through. In the beginning, it does sound a little bit easier. However, as the topic progresses, there may be some sort of type of exercise that you might not be super comfortable with, especially two types, especially the ones that involve a term in the middle of a sequence, which you need to find specifically so you don't have to expand the whole thing, and also exercises that involve a power of n, so a binomial to the power of n. So we don't know the power of the binomial. These are usually the trickiest types of exercises. And the idea of this video is exactly that. Start with the easier types and progress our way towards the hardest one. Also giving you a brief intro to binomial expansions. So the exercises that we're going to work with are the following. Exercise number 0, which is actually not something that you're going to find in an IB exam, so that's why I labeled it 0. Expand 2 minus x to the fourth, but this will serve as a nice little intro for discussing binomial expansions. Now, mentioning the ones that can actually show up in an IB math exam. Find the term next to the fifth in this binomial, that's exercise number 1. Then find the coefficient of the term in x squared for this other binomial, which is a very similar exercise to exercise number 1. The difference here is that we're not addressing or finding the term, but the coefficient. But in practical terms, the difficulty is equivalent. This is one way also to go through a couple of examples of this type. This is a very important type. It's one that shows up a lot. And then we move to exercise number 3, which is to find the term in x to the negative 3 in a combination of two binomials. So we have one binomial times the other one. Then we have this exercise number 4, which is a bit more creative. We need to address in it two specific terms in this expansion. And then lastly, we have another one which, as well as exercise number 4, exercise number 5 also deals with the binomial to the power of n. These last two exercises are usually the ones that students have the most trouble with. So let's just bite the bullet and go through all of these, starting with an intro. Now, one of the best ways that we can introduce the binomial theorem or binomial expansions is starting with Pascal's triangle. I'm going to write it in two different ways, and we're going to prove a few things as we go along. The two different ways are one using integers and the other one using binomial coefficients. How do we build Pascal's triangle? In this row, which is called row number 0, we have a 1. In row number 1, which is actually the second one that we write, we have a couple of 1s over here. Again, we're going to explain where this comes from in a minute. Let's just go through the process first. On the row number 2, which is the third one that we write, we have 1, 2, 1, and we create or we define these coefficients as the sum of these diagonals. So for example, this 2 is the sum of this 1 plus 1. And we continue with this pattern. We have, for example, a 3 here, which is the sum of 2 plus 1. The edges, or the first and the last coefficients, they're always 1. And we carry this process from top to bottom. I'm going to stop here at row number 5, which is actually the sixth one that we write. And I'll label them right here. This is row 0. This is row 1. This is row number 2, and so on and so forth. This 0, 1, and 2, and 3, and 4, they are associated to the power of the binomial that we're expanding. When we expand a plus b squared, for example, and let me do this one manually, or not manually, but actually writing the binomials and foiling, we get a squared plus ab plus ba, which is the same thing as ab, so we have 2ab, plus b squared, where the coefficients 1, 2, and 1 can be found in Pascal's triangle. We're going to mention why that's the case in a minute. Now, we go through the same process when expanding, for example, a plus b cubed, but this time we're not going to do this through foiling. This process becomes a burden when the power is greater than or equal to 3. It starts to be a hassle, right? So that's why, and this is one of the reasons behind using Pascal's triangle when expanding these binomials. So if you were to expand a plus b cubed, instead of getting the coefficients 1, 2, and 1 over here, like we did for a plus b squared, we would have the coefficients 1, 3, 3, and 1, as we see in Pascal's triangle. Now, for reasons to be mentioned in a minute. Now, this solves the problem for the coefficients, but it doesn't address how we can write or lay out the powers of a and b. And what we do is the following. We start with the highest, and by highest, I mean the exponent of the expansion power of a, and we decrease it by 1 as we go from left to right. If you do this from right to left, it works as well, but we're doing this from left to right. So let me just decrease a by 1 as we go from left to right. So a cubed becomes an a squared, becomes an a to the first, which becomes an a to the 0, which is just 1. We put the plus signs over here, and then we do the opposite for b. For b, we're going to start with the highest power, or the exponent of the binomial. But now, if we did a from left to right, we're going to do this from right to left. So b cubed, b squared, b to the first, and then b to the 0. Now, again, b to the 0 and a to the 0, these are just 1. A to the first and b to the first powers, they can be just written as a and b respectively. So our expansion becomes this. Now, why does this work, right? It seems like black magic, right? And it works for a reason to be mentioned after writing this triangle, Pascal's triangle, in a different way. If we write it using binomial coefficients, the explanation makes a lot more sense. Okay, so we're going to, next to these integers 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on and so forth, write the binomial coefficients that's actually represented, or that represents this integer. When writing the binomial coefficients, do know that we start with the row number and the number of the term minus 1. So for example, this is 0, choose 0. That's how we read it, which means that this is the first or associated to the first term in row number 0. This, for example, is 1, choose 0, which means that this is associated to the first term in row number 1. Then we have 1, choose 1, and so on and so forth. Now, one thing that we still need to address, because we didn't mention yet, and I'm going to do this until row number 4, is how to go from, for example, let me just do one more over here, 5, choose 2 to 10. And this is something that we do a lot in probability and combinatorics. We're trying to find the number of ways of choosing k items from n available items. Let me place the formula here first. So this is n factorial over k factorial n minus k factorial, which means for this particular example that 5 choose 2, it is equal to 5 factorial over 2 factorial times 5 minus 2, which means 3 factorial. Now, what is a factorial again? N factorial means n times n minus 1 times n minus 2 all the way to times 1, which means that this is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1, and 3 factorial is 3 times 2 times 1. We can cross out a few numbers here. We can simplify the 4 with the 2, which becomes a 2, and everything is reduced to 10. 10 is the result. There's a simpler way of simplifying these factorials. If you rewrite, and let me place this here, this 5 factorial as 5 times 4 times 3 factorial, given that 3 factorial is the remaining 3 times 2 times 1, and knowing that 2 factorial is just 2, we could simplify it like this. And of course, we would get the same number, the same 10. So this is how we find and choose k. And do remember the definition where this comes from. This is the number of ways we can choose k items out of n. So let's say you have, and by the way, in this case, the order doesn't matter, okay? Let's say you're forming a group of 3 people out of 5 available people. And nobody occupies a different role. Everybody occupies the same role. So the only thing that matters is what group are we forming? We are forming, right? So if you have 5 available people and you want to make a group of 2, in this case, I'm going to use 2, okay? So from 5 people, there are 10 different ways of forming pairs or forming groups of 2, right? This is exactly what 5 choose 2 means. And this ties back to the whole idea behind Pascal's triangle. And this is the most important part. Why is it the case that when expanding, for example, a plus b to the 4th power, we have 6 different ways of choosing 2 a's and 2 b's? Well, we can see that if we draw a small diagram. So what is a plus b to the 4th? This is a plus b times a plus b times a plus b times a plus b. Well, it says here that we should have 6 different ways of selecting 2 a's and 2 b's when foiling, right? Which means that there are 6 different ways of choosing 2 a's from anywhere from here and 2 b's from anywhere from here. And do notice that you can only select either an a or a b in the same or in each binomial to compose that a squared times b squared. So for example, one alternative could be selecting these 2 b's and these 2 a's. And I'm going to copy and paste this a few times because I know that there are going to be 6 possible ways to get that. And the ways are BB, AA, BA, BA. And then if you play with this, you get 6 possible combinations in this foiling process. And this is where this idea of choosing is coming from. Given that this 6 is our 4 choose 2, 2 out of these 4 factors contribute with a B, and the other 2, 4 minus 2, contribute with an A. There are 6 possible ways of doing that. Now, the last thing that needs to be addressed or answered is the following. Why is it that the sum of these 2 diagonals produce this coefficient in the middle? Well, this comes from Pascal's rule, which states that n minus 1 choose k minus 1 plus n minus 1 choose k equals n choose k. Now, do notice that we're adding 2 numbers from the previous row. So, for example, 2 choose 0 and 2 choose 1. So these 2's, they're from the previous row. The sum of them, and k in this case being equal to 0 makes k plus 1 be 1, is equal to the term or the coefficient in the next row, which in this case is 3, choose k. So in our example, n equals 3 and k equals 1. Now, how can we prove this? We can use the definition of a binomial coefficient to write this as n minus 1 factorial over k minus 1 factorial times n minus 1 minus k minus 1 factorial plus, and then we have the second one here, n minus 1 factorial over k factorial, n minus 1 minus k factorial. Now, notice that this is the same as n minus k, in this case, n minus k factorial. And this can be rewritten as n minus k minus 1 factorial, just organizing the terms a little bit. We can copy these fractions again. And by noticing that k factorial is the same as k times k minus 1 factorial, when we reduce the integer by 1, we are moving to the next term in this factorial. So, for example, in this case, n factorial can be written as n times n minus 1 as times n minus 2 and so on and so forth. Or you can pretty much just stop anywhere and place a factorial in the end. because, for example, in this case, this n minus 2 factorial represents the continuation of these products, n minus 2 times n minus 3 times n minus 4 until 1. And we can do something similar over here. This n minus k factorial is n minus k times n minus k minus 1, one iteration more, factorial. And this is going to allow us to write everything under the same denominator, which will be k times k minus 1 factorial times n minus k times n minus k minus 1 factorial. Therefore, in the numerator, we'll have the first n minus 1 factorial multiplied by k plus the second n minus 1 factorial multiplied by n minus k. Notice as well that k times k minus 1 factorial, doing this in reverse now, is equal to k factorial, and n minus k times n minus k minus 1 factorial is equal to n minus k factorial. Also, if you put n minus 1 factorial as a common factor in the numerator, we'll get this n minus 1 factorial times k plus n minus k. So this k over here plus this n minus k over here. The k's cancel out, and in the numerator we get n times n minus 1 factorial, which is just n factorial. And this is precisely the definition of n choose k. All right, so let this serve as an intro to binomial theorem or to binomial expansions. All right, so let's jump to the first exercise in this list, which is actually exercise number 0. We need to expand 2 minus x to the 4th power. This is the simplest type of exercise you can find. You're not going to find it in a past paper in an IB math exam because it is not as sophisticated in order to be inserted in an IB math exam. But this is a nice intro to what we've been discussing over the last few minutes. Now, if we're going to expand 2 minus x to the 4th power, given that 4 is not a very high exponent, we can create Pascal's triangle from rows 0 to 4. It doesn't take that long. We already have Pascal's triangle here, so let's take advantage of that fact. So expanding 2 minus x to the 4th power. Instead of a, we have 2. Instead of b, we have negative x, which means that in this expansion, we will have 1 times 2 to the 4th power plus 4 times 2 cubed times negative x. Don't forget to put the negative also in the place of b to the 1st power plus 6 times 2 squared negative x squared plus 4 times 2 to the 1st power negative x to the 3rd power plus 1 negative x to the 4th power. Now, all there's left for us to do is to simplify this. So for example, 2 to the 4th, that's just 16, plus 4 times 2 cubed, 4 times 8, 32 times negative x, negative 32x, plus 24x squared, plus 8 times negative x cubed, that's negative x cubed. So negative 8x to the 3rd power plus x to the 4th. Therefore, this is our solution for exercise number 0. Now let's move to exercise number 1. In exercise number 1, we need to find the term in x to the 5th in the expansion of 2x minus 3 over x squared to the power of 8. Now, given that we have a binomial to the power of 8, it is not practical to create Pascal's triangle up to the 8th row. It takes too long. So, and by the way, that's not the idea for this exercise. It's not a sophisticated process. A better idea is to realize or to understand how each term is created. When you're expanding 2x minus 3 over x squared to the power of 8, we will have the coefficients, the binomial coefficients from the 8th row of Pascal's triangle multiplied by a. And what do I mean by a? I'm referencing a general or generic binomial expansion, a plus b to the nth power. We always have n over here, choose k, and this k is a placeholder that goes from 0 to 8, 2x to the 8 minus 0, or n minus k, times b, which is negative 3 over x squared to the power of k. We can see this pattern emerging in every expansion that we did previously. For example, what is a plus b cubed? This is 3, choose 0, a to the 3 minus 0 times b to the 0, which is just 1, b to the 0 is 1, plus 3, choose 1, which is just 3, a to the 3 minus 1, b to the first power, plus 3, choose 2, which is 3 again, a to the 3 minus 2, b squared, b to the 2, plus, and then we finish with b cubed. This pattern dictates a binomial expansion. So we can write a few terms in the expansion of 2x minus 3 over x squared to the 8th as well. So again, a choose 0 to x to the 8th, negative 3 over x squared to the 0, plus the next one will be a choose 1 to x to the 8 minus 1 times negative 3 over x squared to the first power plus dot 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 all the way to a choose 8 to x to the 8 minus 8 negative 3 over x squared to the 8th power. Now, one of these terms will have x to the 5th in it, but what is that term? In this case, we can see more clearly because it's already showing up, but I'll teach you a method in which you can find through an algebraic process which keeps you from expanding the whole thing. Now, let's just see what we have in front of us right now. A choose 0, this is just 1, 2x to the 8th, it's the same as 2 to the 8th, x to the 8th. Don't forget to raise 2 to the power of 8 as well. Therefore, 256 x to the 8th times 1. So this first term right here is 256 x to the 8th plus a choose 1. Anything choose 1 is just that anything. In this case, it's 8. Now we have 2 to the 7th, x to the 7th power times negative 3 to the 1st over x squared to the first power as well. And right here, we can already see the term in x to the 5th. And that is because this x squared will simplify with this x to the 7th, becoming an x to the 5th. Now, again, this was easier because it was already in front of us, but we can make this exercise a little bit more complicated if we were to find, for example, the term in x to the negative 1, which means something over x, which is somewhere in the middle here. Now, why is this a little bit trickier? Because we cannot see it, and we can either expand the whole thing or use a better algebraic process, which is what we're going to do right now. Just restating something that was mentioned before, the expansion of this will involve terms that look like this. A choose k, 2x to the 8th minus k, times negative 3 over x squared to the power of k. We're going to raise each individual number or variable to the given power. So we're going to have a choose k, which is the binomial coefficient, times 2 to the 8th minus k, times x to the 8th minus k, times negative 3 to the k over x squared to the k. Now, x squared to the k is the same thing as x to the 2k. And when we divide numbers with the same base, we subtract the exponents. Therefore, we can rewrite all this as a choose k, 2 to the 8th minus k, times x to the 8th minus k minus 2k, which means 8 minus 3k, times negative 3 to the k. Now remember, we're trying to find the term in x to the negative 1, so we would like this exponent, which is the exponent of x, to be equal to negative 1. Now, I know this is a sophisticated process, but this is the most accurate method you can use without guessing and checking anything. So again, we want our 8 minus 3k to be equal to negative 1. So we have an equation to solve. 9 equals 3k, so k equals 3. Therefore, we need to choose a term which has k as 3. So we need to go back here and substitute our k by 3. Therefore, we're going to have a choose 3 times 2x to the 8 minus 3, which means 5, negative 3 over x squared cubed. By the way, a choose 3 is 56. We have 32x to the 5th over here, and over here, negative 27 over x to the 6th. When we multiply all of these, we get negative 48,384 x to the negative 1, or negative 48,384 over x. Now remember, this is not matching the previous answer because right now we're finding a different term, one that has x to the negative 1. All right, so let's jump to the next exercise. All right, so a very similar exercise. The difference here is that he's asking for the coefficients as opposed to the term. Therefore, we're going to get the answer as something times x to the something, and only the coefficient, which is the number that multiplies x, is going to belong to the answer. We're going to write the answer with only that. Now, despite the fact that this exercise is very similar to the previous one, it serves as an extra practice for that type of exercise, which is quite common. So let's get to it. We know, as it was mentioned in the previous exercise, that any term in this expansion will have the following recipe. 6 choose k, x cubed to the 6 minus k times negative 2 over x to the k. Now, can I guess and check values for k until I get x squared as a result, something times x squared? Yes, you can, it's fine. However, I'm going to develop this using a more sophisticated process, which was the one mentioned before in the previous exercise. I'm going to raise x cubed to 6 minus k, negative 2 to the power of k, and x to the power of k as well. And we're going to simplify this as much as possible, which means that we'll get 6 choose k. We don't do anything with this, not yet. X to the 3 times 6 minus k. Remember, when you have a power over a power, we multiply the exponents. Then we have negative 2 to the k over x to the k as well. We're going to simplify the powers of x. This one being 18 minus 3k, and this one just being k. We need to subtract these exponents given that we have a division. So we get 6 choose k, x to the 18 minus 3k minus k, which means 18 minus 4k times negative 2 to the k. Now we want this exponent to be 2. We want the coefficient of the term in x squared. Therefore, if we want 18 minus 4k to be equal to 2, we can build this equation and solve it, finding 4 as an answer, which means that the actual term will be 6 choose 4, x cubed to the 6 minus 4, negative 2 over x to the 4th power. Now 6 choose 4 is 15 times x to the 6th, which is x cubed squared, times negative 2 to the 4th power, which is 16, over x to the 4th. Now these simplify. We get x squared as expected, leaving as our final answer 240x squared. Now, we do need to address the question, which is to find the coefficients. What is the answer for this question? The answer is 240. And that is it. Let's jump to the next one. All right, so let's jump to exercise number 3. We need to find the term in x to the negative 3 in the expansion of a product of two binomials, x minus 1 cubed times 1 over x plus 2x to the 6th power. When you have this type of question in IB math exams, one of the binomials will be a simpler one. And in this case, I am, of course, referring to x minus 1 cubed. Now, this expansion can be done quite fast. If you remember the third row of Pascal's triangle, which we can see right here, 1, 3, 3, 1, we can use it to expand x minus 1 cubed. So we have 1, 3, 3, 1. We have x cubed, x squared, x, and x to the 0. And we have negative 1 cubed, squared, now from right to left, to the first, and to the 0th power. Therefore, this whole expansion can be simplified to x cubed minus 3, x squared plus 3x minus 1. Now, this is for me to say that within this exercise, at least one of the binomials will be a simpler one. So let's already replace this x minus 1 cubed by this. And now let's focus on the second part. What I want you to realize in this expansion is that as you're expanding it, the powers of x will jump, which means increase or decrease depending on the order that you choose, in steps of the difference between the exponents. We have x to the first power and x to the negative 1. So they're going to skip in steps of 2. Now, what am I trying to say here? What do I mean by this? If you write the first few terms, and let me just write the first 3, you realize just that. You notice that after simplifying, these terms, which give you 1 over x to the sixth, which by the way is the same as x to the negative 6. The second one gives us 12 over x to the fourth, which is the same as 12 times x to the negative 4. And the third one gives us 60 over x squared, which is 60x to the negative 2. Now we can spot a pattern here. These exponents are increasing with a common difference of 2 until we get to the last one, which is 64x to the sixth power. So we can see that the powers of x range from x to the negative 6 to x to the sixth power, which tells us that to produce terms in x to the negative 3, we need to make combinations through these multiplications, which, well, will give us x to the negative 3 as a result. And the combinations are the following. 3x times whatever this term is, which we're going to find in the next step, or x cubed times this term, which we're going to find as well. We actually did find this one or these ones, but we're going to find them again, just for the sake of this explanation. Now, what is this first one? This is our 6 choose 0 times 1 over x to the sixth times 2x to the 0, which is just 1. What is the second one? This is 6 choose 1, 1 over x to the fifth power times 2x to the first power. Now, creating these products gives us, and by the way, just simplifying these before, we have 1 over x to the sixth and 12 over x to the fourth power. Now, the product in purple gives us x cubed times 1 over x to the sixth, which is 1x to the negative 3. Now, the second one gives us 3x times 12 over x to the fourth, which is the same thing as 36x to the negative 3. Therefore, the term in x to the negative 3 is x to the negative 3 times 1 plus 36x to the negative 3, which is 37 times x to the negative 3, which, by the way, is the same thing as 37 over x cubed. All right, so that's all there is to this exercise. If you wanted to expand the whole binomial 1 over x plus 2x to the sixth to see this foiling process, you could, if this power is not that high. Now let's jump to the next exercise. Okay, so now we have the following exercise. Find the exponent n, given that in the expansion of root 2 plus 2 over x to the power of n, the coefficient of the term in x to the negative 5 is 4 times the coefficient of the term in x to the negative 1. So clearly we must find in this expansion two very specific terms, one in x to the negative 5 and the other one in x to the negative 1. Now we need to know, when dealing with this type of exercise, how to find these specific terms in this expansion without expanding it entirely. And in this case, given that we don't even have the exponent, which is just an integer n, it's not even given to us, we actually have to find it, we don't even have the possibility of expanding it entirely. So remember that in a binomial expansion, all terms will have the following structure: n choose k, a to the n minus k, b to the k. Now in this case, a is root of 2 and b is 2 over x. We very often call this the term k plus 1 or t k plus 1, which means that if you were to expand root 2 plus 2 over x to the power of n, you would get n choose 0, root of 2 to the n minus 0, 2 over n to the 0, which is just 1, plus n choose 1, root 2 to the n minus 1, 2 over x to the first power, plus dot dot dot, and this continues until k is equal to n. Now, which of these terms is the term in x to the negative 1? And which of these terms is the term in x to the negative 5? We can actually spot the term in x to the negative 1. It is the one where k is equal to 1. This k over here, which means this k over here. And let's take a closer look at this term. We have n choose 1, which is equal to n. And by the way, anything choose 1 is just that anything. You can prove it using the definition of a binomial coefficient, where n choose 1 is equal to n factorial over 1 factorial, which is just 1, times n minus 1 factorial. We can rewrite the numerator as n times n minus 1 factorial, and then we can simplify the n minus 1 factorial from the top and the bottom, or the numerator and denominator. So we get our n. But continuing over here, we have root of 2 to the n minus 1 times 2 over x. Now, as mentioned before, this n choose 1 is just equal to n. Therefore, we can rewrite this as 2n root of 2 to the n minus 1 over x. Or, and this is the same thing, 2n root 2 to the n minus 1 times x to the negative 1. So this is the term in x to the negative 1. Now, how can we find the term in x to the negative 5? If we continue with this expansion, at some point we're going to get n choose something, and let's see what that something should be. Root of 2 to the n minus that something times 2 over x to that something. What is that something? We want this exponent to be 5. Why is that? Because if this is 5, that means that we're going to get an x to the negative 5, which is exactly the term that we're looking for. Therefore, we should look for the term where k is equal to 5, giving us this. So for k equals 5, we have n choose 5, which is a bit more complicated to simplify when compared to n choose 1, times root of 2 to the n minus 5 times 2 to the 5th, which is 32, over x to the 5th, which is just x to the 5th. Now, let's simplify n choose 5 as much as we can. We have n factorial over 5 factorial n minus 5 factorial, which can be written as n times n minus 1, n minus 2, n minus 3, n minus 4 times n minus 5 factorial over 5 factorial times n minus 5 factorial. We can simplify these n minus 5's factorial, which will give us n minus 1 all the way to n minus 4 over 120. Now let's insert all that over here. So there we have it. We're not going to simplify at this point. And by the way, let me write this as 32x to the negative 5. We're not going to simplify this right now because we didn't use one information from the exercise yet. And we're going to simplify as we use that piece of information, which is the coefficient of the term in x to the negative 5 is 4 times the coefficient of the term in x to the negative 1. Now, the coefficient of the term in x to the negative 5 is all this without the x to the negative 5. And the coefficient of the term in x to the negative 1 is all this without the x to the negative 1. Therefore, we're going to build an equation from that. So this is what we have. Given that the coefficient of x to the negative 5, or the term in x to the negative 5, is 4 times the coefficient of x to the negative 1, we have this equation to solve. Now, there are a lot of things to simplify right now, starting with this 32 over 120, which is the same as 4 over 15. We can also simplify 4 and 4 over here. There are a couple of n's that we can simplify as well, and we can cross multiply this 15 to the right hand side. So we have n minus 1, n minus 2, all the way to n minus 4, root 2 to the n minus 5, which is the next thing that we're going to simplify, equal to 30. Don't forget this 2 over here, root 2 to the n minus 1. Now, we can divide both sides by root 2 to the n minus 5. Just be careful when you apply exponent rules. We need to subtract the exponents. In this case, we get n minus 1 minus n minus 5, and this is equal to 4. Meaning that this whole thing will become root of 2 to the 4th power, which is equal to 4. By multiplying 4 and 30, we get 120. So this whole equation is reduced to n minus 1, n minus 2, n minus 3, n minus 4, equal to 120. Now, this is the part that you use your GDC to solve it. You can make an educated guess as well, given that this is a factorial. This is the same as 5 times 4 times 3 times 2 times 1, but you can use your GDC as well. This is a paper 2 style question. N is equal to 6. We should get an integer, so everything looks fine, and n equals 6 is the answer. Now let's jump to the next one. All right, so we have in front of us a binomial for which we were not given the exponent. We have 1 plus ax squared to the power of n. The purpose of this exercise is for us to find not only that exponent, n, which is a constant, it's an integer, but also a. Now, provided that 1 plus ax squared to the power of n is equal to 1 plus 45x squared plus 900x to the 4th, and so on and so forth, where a and n are integers, we need to find a and n. Now, the binomial theorem states that whenever you're expanding a binomial such as p plus q to the power of n, we get n choose 0, which, by the way, this is just 1, p to the n minus 0, which is the same as p to the n, and q times q to the 0, which is 1, plus n choose 1, which is equal to n, p to the n minus 1, q to the first power, plus n choose 2. We are going to simplify n choose 2 in the next step, times p to the n minus 2 times q squared plus dot dot dot. Now there's no p and q in this binomial. There's 1 and there's ax squared. So this guy right here is actually our p, and ax squared is q. Therefore, the expansion of 1 plus ax squared to the n, it is equal to n choose 0, which we're going to replace by 1, times a to the n minus 0 times q to the 0, which is just 1. Now do notice that 1 to the n is also 1. So the whole thing, this whole term, will just be 1. So this guy right here does not provide us with any valuable piece of information, but the next one will. On the next term, we have n choose 1, which is equal to n. So we're just going to replace this by n times 1 to the n minus 1, which is equal to 1, times ax squared to the first power, plus n choose 2, which we're going to simplify right now using the definition of a binomial coefficient. This is n factorial over 2 factorial times n minus 2 factorial. N factorial can be rewritten as n times n minus 1, n minus 2 factorial, which can be simplified with the n minus 2 factorial in the denominator. All of this times 2 factorial. This 2 factorial can be replaced by 2 as well, because, well, 2 factorial is equal to 2. Therefore, n choose 2 is n minus 1 divided by 2. So let's replace it right here. We have n minus 1 divided by 2 times 1 to the n minus 2 times ax squared to the second power, plus dot dot dot. Now, again, 1 to the n minus 2, this is just 1. And now we can compare the terms that we got in this expansion, with what was given to us by the exercise. Comparing the first one does not provide us with any meaningful information, as mentioned before. 1 is indeed equal to 1. That's fine. We know that, right? But we can say that n times ax squared, well, this is equal to 45x squared. Therefore, 45 is equal to n times a. We cancel out the x squared, or we just ignore it. We're just comparing the coefficient, not the term itself. But if you compare the term itself, it gives us the same thing. You can just cancel out the x squared. And now comparing the 900x to the fourth with this, which, by the way, simplified, gives us n minus 1 over 2 times 1 times a squared x to the fourth. Careful, because this squares both this 2 and this 1 in the exponent of a. This allows us to state that 900 is equal to n minus 1 over 2 times a squared. So we got a system that we need to solve. We can solve this by substitution. You can replace a by 45 over n into the second equation, which gives us 900 equal to n minus 1 divided by 2 times 45 over n squared. We can cross multiply this 2, giving us 1800 equals to n minus 1 times 25. All of this divided by n squared. And by the way, we can simplify a n from here with 1 from here. Cross multiply the n. So we have 25n minus 25. After solving this equation, we get n equal to 9. Now, in order to find the constant a, we can just replace this n value into any of the two equations that we have in our system. And it's much easier, of course, to do it with this. Now, a is 45 over the 9 that we got. Therefore, a is equal to 5. Now, there you go. This is all there is to it.